In this video, we're going to look at the gradient of the chord, we're going to look at the gradient of a tangent, and we're going to look at differentiation from first principles. Now, the most important thing to remember when you're doing this is remember you cannot do differentiation that you've learned in C1 and C2, okay, or C3, C4. What we're doing here is from first principles. You do not, essentially, none of that stuff that you've learned has been proven yet. All that stuff you learn is proven from differentiation from first principles or from the definition of what derivative is. So you don't know any of that stuff. You get 0 marks if you do the derivative like dy dx of let's say x squared is 2x, things like that. Okay, so let's get started. We're going to find the gradient of a chord. Now, a chord of a curve is essentially just a line joining 2 points on a curve. So a chord is similar to a chord in a circle. Let's say I had a curve like this, and the chord joining the point. And here we're using, I mean, this is not this, but let's say 2 points there and there. The chord joining those 2 points is just a straight line going through those 2 points. Okay, so let's look at example 1. Graph this equation: y equals x squared minus x plus 2. Find the gradient of the chord from the point where x equals 1 to the point where x equals 1 plus h. Now, we remember, to work out the gradient, we do change in y over change in x. So in this case, I'm going to write it like this. I'm going to use function notation. So my change in y is f of x plus h minus f of x. So, and my change in x, well, what's my change in x? I'm going from 1 to 1 plus h. So my change in x is always going to be h. So this is what the normal equation we're going to be using for working out gradient. You can just, if you want to, you could do delta y over delta x, and then do change in y, change in x. But you still have to, essentially, you'll be doing exactly the same thing here. So this is what we're going to be using. This is my change in y. So this is my y coordinate for x plus h. This is my y coordinate for x. And this is my change in x, because think about it, I'm always, in all these examples, we're going to go from something like 1 to 1 plus h, or 2 to 2 plus h. So what's the difference between 1 and 1 plus h? It's just h. So this is my change in y, this is my change in x. All right, so let's work out what this is. So the first one, so I've got f of x plus h. So in this case, I don't mean your x is 1. So this is this. 1 plus h is here. So I need to work out f of 1 plus h minus f of 1 over h. Okay, so 1 plus h, we just have to, so how do we work out f of 1 plus h? We just plug it into here. So it's 1 plus h squared minus 1 plus h. Notice all I'm doing is substituting 1 plus h into the x, plus 2 minus f of 1. So when I plug in 1 into here, well, let's just work it out. So 1 squared is 1, minus 1 plus 2, so 1 minus 1 is 0, plus 2 is 2. So it's positive 2, but we're doing the minus positive 2, so it's just minus 2. And it's all still over h. All right, so all we need to do now is expand and simplify. So 1 plus h squared is just 1 plus 2h plus h squared minus, and then let's minus 1 minus h plus 2 minus 2. Right, these we already see, these will cancel out, over h. Let's simplify this. Well, we've got those two cancel each other out. Those two cancel each other out. The minus 1 and the plus 1 cancel each other out. So what do I have? I've got h squared plus 2h minus h. That's just h squared plus h over h, which just simplifies to h plus 1. I'll just do the cancellation. That's it. That's the gradient of the chord joining the points 1 to 1 plus h. So this graphically, what this would look like, of course, essentially you're thinking of, well, something like this. So this would be, I mean, of course, this isn't this curve, but imagine, so this would be your 1, and this here, there's a gap of 1 plus, there's a gap of h to 1 plus h. So we found the coordinate at 1. Well, that was just 2. So obviously this doesn't follow this graph, but this is we find the coordinate at 1 plus h. We do that y, take away this y over the change in x, which is just h. That's what we're doing. Okay. Now let's look at the gradient of a tangent. So let's just quickly look at this diagram. So what we worked out, let's imagine you wanted to work out the gradient of the tangent at P. Essentially, that's also the gradient of the curve at P. It's the same thing. How do we work out the gradient of the tangent at P? Well, you could, I mean, I think in the past what you do is you might have just drawn a line and then worked out that gradient. But we can't do that, that's just an estimate. We want to be exact. And drawing by hand is never exact. Okay, so you say, oh, I know how to do that. I just do differentiation, but we don't know how to do differentiation. We haven't invented it yet. So what do? Well, let's estimate this. Let's estimate the gradient of this tangent at P, which is this black line. Well, one way of estimating it, we say, let's use a chord, because we know how to do chord. We just did it in the previous example. So we know the equation of the curve, by the way, and we know the coordinate of P. So if we take any Q1, so for any gap h, and then we can work out this coordinate, then we can work out the gradient of this line joining P and Q1. for some value, fixed value of h. So, well, that's an estimate. That orange line is an estimate, but can we make a better estimate? Well, if we make this point q1 closer to p, so let's make it q2, and then we do the gradient of that chord joining q2 and p, that's even better estimate to the gradient of a tangent. So what have we done? Essentially, all we've done is we've made our h here smaller. We've made our change in x, originally this, imagine that was h, now we've just made it smaller, and that gives us a gradient is even more accurate. And then q3, the blue line, is even closer, it's an even better estimate for the gradient of a tangent. So what are we doing? So all we're doing is essentially, to find the gradient of this tangent, we make our h from what we did before tend to 0. So in general, the gradients f at that point, so let's say f prime of x at any point x, the gradient at a point x, what do? Well, part of what we do is we'll work out the gradient of the chord. Well, we know how to do that. It's f of x plus h minus f of x over h. And then we make this h tends to 0. So it's the limit of this as h tends to 0 is the gradient at this point x, whatever that x is. Now, all this limit as h tends to 0 mean, just think about, okay, what does this thing, essentially, all it's saying is, what does this thing go to as h tends to 0? There's more to it than that, but we're not going to go into more detail. You might, if you do a maths degree, you'll see more of that. Okay, so what our limit really is. So essentially, just think about this is all this is saying is my gradient at the point x is the gradient of the chord as my h, as my gap tends to 0. So let's look at a couple of examples. So graph as equation y equals x cubed minus 2x minus 3. Find the gradient of the chord from the point where x equals 2 to the point where x equals 2 plus h. Well, do exactly what you did example 1. So pause now and try this yourself, okay? All right, so all we need to do, so remember, f of x plus h. The gradient of the chord is f of x plus h minus f of x over h. So in this particular example, it's 2 plus h here and 2 here. So we're doing f of 2 plus h minus, because my point f of 2 over h. We need to work out what these things are. Well, we have to plug in 2 plus h into this. So 2 plus h cubed. Now sometimes minus 2 lots of 2 plus h. Now in a more difficult example, you might have to the power 5 to the power 6. They just use your binomial that you've learned in C2. 2 plus h minus 3. So all I've done is I've plugged in 2 plus h. I've worked out f of 2 plus h, which you just plug in 2 plus h for your x. So that gives me 2 plus h cubed minus 2 lots of 2 plus h minus 3. And then I have to plug in 2 into here. Well, let's just work that out. So then I've got the minus, which is that minus, then plug in 2 here, that's 8 minus 4 minus 3. 8 minus 4 is 4, 4 minus 3 is 1. Okay, and it's still all over h. So let's just check that. It's 8 minus 4, which is 4 minus 3 is 1. Okay, so now we just need to multiply this out. So let's work out 2 plus h cubed. So that is, to work this out, I'd say the easiest way to do it is multiply out 2 of the brackets, because this is 2 plus h times 2 plus h times 2 plus h. Well, 2 of the brackets gives me 4 plus 2h plus 2h, which is 4h, plus h squared. And then that's times, now I've still got one of the brackets left, 2 plus h. And while we're at it, let's multiply out the other brackets. So it's minus 4, minus 2h, minus 3, minus 1, and still all over h. If you don't actually want to write this as a fraction every single time, you can just work this out separately and then put it as a fraction. In the end, let's multiply this bit out. So this is actually quite simple. Okay, I'm gonna, instead of doing all of this times 2 and then all of this, actually it's all of this times 2. So it's 8 plus 8h plus 2h squared. Then it's all of this times h. So it's just times, so it's plus 4h squared plus h cubed. Then I've still got the minus 4. And I've run out of space, so I'll write it. Or actually, I can make this smaller. Let's just make this a little bit smaller. And I still got, so I've multiplied this out. So I've still got minus 4, minus 2h, minus 3, minus 1. In fact, I could have simplified the minus 3, minus 1, and the minus 4. Actually, let's leave that anyway. So instead of drawing out, let's simplify that last bit so you don't have too many terms. So minus 4, minus, that's another minus 4, it's minus 8. So minus 2h, minus 8. And still all over h. Well, let's simplify this. So let's just think, things should cancel. So that 8 cancels that 8. So plus 8 minus 8. And what else do I have? Well, I've got an h cubed. There's nothing that cancels the h cubed. Okay, nothing else will cancel each other out. Let's just simplify this. So I've got h cubed. That's that one. Then let's look at my h squared. So I've got 4h squared here. I've got 2h squared here. That gives me 6h squared. Unless I'm mistaken. Plus 6. h squared. So let me just check this. So I multiplied all of this by 2, so h plus 8h plus 2h squared. Yeah, they multiply all of it by 4, so by h, so 4h plus 4h squared. So always double check this because you can make mistakes there. 4h plus 4h squared plus h cubed. Yeah, that's all fine. Okay, so I've got h cubed plus 6h squared, and how many h's do I have? I've got 8 plus 4 minus 2, which is 10. So plus 10h, all divided by h. That's simple. That's h squared plus h plus 10. Okay, that's that done. Now part 2. Hence find the gradient of the tangent when x equals 2. Now when a question says hence, it means use the previous part, okay? So we're not going to do this from scratch again. So hence find the gradient of the tangent when x equals 2. Well, we know how to do this. What did I tell you? The gradient f prime of x, the gradient at x, is limit as h tends to 0. So let me just f of x plus h. By the way, this thing I'm writing is not given to you. You do need to remember this. Or you could just remember, okay, I just work out the gradient of the chord and then think about the h tending to 0. You don't need to remember exactly this formula if you remember the process. So we're working out the gradient of the tangent at point 2. Well, so I'm working out f prime of 2. So that's not x, that's 2. Well, that is the limit as h tends to 0 of f of 2 plus h minus f of 2 over h. But I've already worked this out. We've already got that. So look, that's the same as that. That's the gradient of the chord. We've already worked that out. That's this. So this is the limit as h tends to 0 of this. H squared plus h plus 10. Well, let's look at this. Well, as h goes to 0, just think about what, as h goes to 0, what does this go to? Well, if h is going to 0, then h squared is still going to be, well, 0 squared. You could essentially just plug it in. As h tends to 0, well, this goes to 0, h goes to 0, and 10 stays 10. So this is equal to 10. And we're done. Now, if you want to do, we can double check by differentiating. So we can actually differentiate this. So let's, if I know this is this dy dx. By the way, I could have, there is a Leibniz's notation, they would use delta y over delta x instead of f of x plus h minus f of x. So this is your change in y, this is your change in x. Now this goes to, this tends to dy, or essentially, actually, instead of writing tend to, the limit of this as delta x, so your change in x goes to 0, is equal to dy dx. And that's where dy dx comes from. This is using Leibniz's notation, this is using Newton's notation. Newton uses f's, Leibniz uses dy dx. Okay, so essentially, if you do essentially change in y by change in x, delta just means a change, delta just means a change. And as this change in x goes to 0, this whole thing, the limit of this as delta x tends to is dy dx. That's where dy dx comes from. Anyway, let's just double check our answer that we get 10. Let's work out the gradient. Let's work out, so if this is a dy dx, it's just simply 3x squared. Now this is my checking, I'm not getting any marks for this, it's just to check. So it's 3x squared minus 2. And we're working out dy dx at 2. So plug in 2 here. So I get 2 times 2, which is 2 squared, which is 4, times 3, which is 12, minus 2 is 10. So at 2, dy dx is equal to 10, which is what we had. So same answer, so it's work. Okay, finally, example 3. Differentiation, again, as I said at the beginning of the video, when they say differentiation from first principles, doesn't mean differentiation as you did in C1 or C2. That means doing exactly what I've just done. So when they say differentiate, if they say just differentiate this from first principle at the point where x equals a, do exactly what I've done, okay? So we want to find the gradient of the curve at the point where x equals a. Can't differentiate. So that all that is the, so let's just remind ourselves what the derivative, or the definition of the derivative f prime of x, the derivative, this just means the derivative at the point x. We defined it as the limit as h tends to 0 of f of x plus h. By the way, this is, I'm not just making this up. I don't do that, but this is very common. You can find this online. I mean, you can find this everywhere. Okay, so this definition. So what we're doing, we're working out the gradient at when x equals a. So just plug in a. So f prime of a, the gradient at a, is f of a plus h. Wait, I forgot the limits. So limit, let's put that in. I'm only going to put it in limit as h tends to 0 of f of a plus h minus f of a over h. So I need to work this bit out now. So I'm gonna stop writing limit as h tends to 0 f prime of a. I'm gonna write that in the end, but right now all we need to do is work out what this is. So f of a plus h minus f of a over h. So all that means is we need to plug in a plus h into my equation. I need to plug in a into my equation and see what we get. So by the way, of course, I'm defining this, instead of using y here, I'm just going to imagine f of x was equal to this, right? So a plus h into that, so it's a plus h squared plus 2 lots of a plus h minus 3, and then plug in a into that. Well, that's just simply, I'm going to, as a minus, that's that minus, plug in a into that, so I'm just going to write it as a squared. I'm going to write it like this with the brackets so I don't make mistakes with my negatives, and it's all of that, of course, it's divided by h. And of course, if you don't want to write divided by h, because the tricky bit here is this bit, the dividing by h is not a problem. So let's just, what's that equal to? Well, let's multiply out. So that bit there is a squared plus 2ah plus h squared plus 2a plus 2h. I'm multiplying this out now. Minus 3 minus a squared plus 2 minus 2a plus 3. So I think let's just double check. So a squared plus 2ah plus h squared plus 2a plus 2h minus 3 minus a squared minus 2a minus 3. That's fine. That's all of that divided by h. Now we just need to simplify and do the actual cancellation divided by h. So let's look at this. Hopefully some things just cancel each other out. So we've got plus 3 minus 3. We've got plus 2a minus 2a. We've got a squared and a minus a squared. They cancel each other out. So what do we have left? We've got h squared plus 2h plus 2ah. So let's simplify that. We can gather my terms together. I'm going to factorize out the h from those. So it's plus h. And inside I've got 2a plus 2. Now you could have factorized out the 2 if you wanted to as well, but you'll see the reason why I did this is now the h just cancelled out, and that just gives you h plus 2a plus 2. Okay. Right, that's pretty simple. Finally, so we've worked out this bit. We worked out this bit in here. That is 2h plus 2a plus 2. So let's actually now do the limits. So f prime of a is equal to the limit as h tends to 0. Now I'm not going to bother writing it, of this. But this, we've just worked out, is this. So of h plus 2a plus 2. Now, what does this go to as h tends to 0? Well, h tends to 0. As h tends to 0, h tends to 0. So that's 0. 2a, well, it's not affected by the h, is it? 2a is still 2a. H going to 0 doesn't affect 2a. Same thing with the 2. So this answer is 2a plus 2. And we're done. That's it. That's my gradient differentiation from first principles. So let's look at it all in one go. Again, when I say f, again, I know they didn't put f's in the question. They put y, but you should be comfortable just saying, okay, let's just make this y and f of x. Okay, so it's changing y over changing x as h tends to 0. That's all I'm doing. I plug in a plus h into my equation. I plug in a into my equation. I did the subtraction divided by h, and then did the limit as h tends to 0. Okay, so that's it for now. Go away, try some exam questions. There is another part of calculus, of course, improper integrals. We'll do that in a separate video.